Let's take a look at a few more examples using pointers in C and C++. Here we have an example of a function declaration that takes pointer to an array of integers, and the name of this pointer is zip codes, and also specifying the size of this array of zip codes. In our main function, we declare some double variables, and we call them price of different products. And if we'd like to obtain address of these variables and store them in pointers, you can see that we of course need to use asterisk as a type modifier for the pointer, a variable that then can accept the address of a variable. We can compute differences between pointers. So we have, for instance, pointer to two of these objects in memory, and of course these objects reside at different memory locations. None of the variables ever overlap in computer memory, so they have unique memory allocation, and sometimes it's useful to determine how far apart in terms of computer memory space these objects are located. So you can subtract one pointer from another and find out. The result of this is actually number of doubles, not bytes, simply how many doubles apart these two pointers are. And then we can say that the distance between two double variables in memory is, and we can print the result. What else can we do with pointers? We can use simple arithmetic operations to move pointer around. So the pointer is a variable, and we can use it to navigate to different locations in memory. Here we create a pointer named zip codes, and we dynamically allocate 5 integers in memory using the new operator. So this syntax allows the program to dynamically allocate whatever number of integers you want. In my case, I'm allocating 5 integers dynamically. And the new operator returns back the location of the first integer in memory. So this is an example of this dynamic memory array, and I am here allocating 5 integers, right? So this is a block of memory that has 5 individual integers. And when I allocate it like this as new block of 5 integers, the actual content is unknown. It's just a random combination of zeros and ones that happen to be in that memory. So then, once the new operator returns an address of the first integer, right? So the new operator, what it does, it allocates, number one, it allocates all of this memory that provides enough space for this many integers, and then returns an address to the first element in this block of integers. So this pointer will get address of the first integer in this memory block. If we're using subscript operator, using the square brackets, we can access individual elements of this dynamically allocated array of 5 integers by using index 0, 1, 2, 3, 4, 5, and so forth. And of course you can see that the indexing is 0 based. So basically, to access the initial element in this array, you have to use index 0. Subsequently, the last element in this dynamically allocated array has an index 1 less than the number of elements in this dynamically allocated array, simply because it's counting 0, 1, 2, 3, 4, and that's altogether 5 unique elements. So using this type of access to memory by using subscript operator, it automatically dereferences the pointer, and having this pointer, we can use it as a dynamic array and just say, okay, let's store these values in 5 different locations of this array. So the result is that these numbers are now stored in this memory, and you can see that I'm showing those newly updated values. So initially this variable, this pointer variable, is pointing to the first element in the array, right? So this is pointing to the first element in the array. However, it's possible to change the location that's stored in the pointer, and we can say plus plus, for example. If we say plus plus, then the pointer advances to the next location, to the next element in this dynamically allocated array. So for example, if then we say let's print, like increment this pointer and print the value, I'm expecting that this will be the value that is printed here after we incrementing the pointer, because now this pointer is pointing to the new location, to the next location compared to the previous location. So both increment and decrement operators are available for pointers, and you can advance pointers when they're pointing to the block of elements in memory, and both plus plus and minus minus operators are available to move them around. In addition, we can simply say plus whatever number of steps we want. So if after setting this pointer to this location, then we apply +2, apparently what happens is that after this is done, now this pointer is pointing to this location in memory, and if we print it, it should be printing right here. This statement should be printing this value on computer screen. Another demonstration of it is that when we use so this example here is using dereference operator, the asterisk in front of the pointer, to navigate to the location to which the pointer is pointing to. But when we use square brackets, the subscript or index that we use, which is 0-based, can also be negative. So at this stage right now, apparently our pointer is pointing to this integer in memory. So naturally, if I say -3, the compiler will calculate the actual location of this zip code with subscript -3 as -1, -2, -3. So apparently this statement should be printing this value on computer screen. We can pass information to a function using the pointer. So here we have the pointer, and we can, as you can see, this function was declared right here at the top as a function that is taking a pointer to an integer and also takes the size of the block of memory which this pointer is pointing to. Remember that there are two things that the pointer knows. First of all, it knows the address. So pointer, of course, has the address and knows the address of an object. But in addition to this, the pointer knows that it's a pointer to a specific type. So it knows that at this address there is this integer which is made up of, for example, 4 bytes, if it's a 32-bit integer. So this is all the knowledge that the pointer has. However, if we would like to use this pointer as a pointer to the entire block of memory that potentially has more integers in there, we must keep track of the size of the block that we would like to use. And of course, in our case, this is the size of the block, and we have to use a separate variable to specify how big this block really is, because the pointer has no knowledge about how many really values it's pointing to. It knows the address of one of them, but it doesn't know how many it can actually access. So it's very typical to see part of function declaration is some sort of pointer, and the next parameter would be the size of the block of memory which this pointer can navigate and step through in any way it wants. So here we demonstrate a function call to function process zip codes, and the pointer is passed as the first argument of the function. And here we say, okay, we have 2, the size of this block of memory is 2. So once again, according to our prior manipulation, if the zip codes pointer is pointing to this integer in memory, we say that let's assume that the block of memory on which this process zip codes can operate is basically this size right here, right? So this is this size, 2 elements. We say to this function, your block of memory is made up of 2 integers, and we pass a pointer to the first integer in this memory block. Of course, there could be other elements in memory which are still accessible through negative indices and other things, but apparently the intention here is to limit this function to use only an array of 2 integers, and we pass the pointer to the first element in this block of memory. There are many reasons why we need to understand pointers and use them in our code. As we've seen in our examples, accessing individual characters inside a string literal requires use of pointer. If we want our functions to be able to access objects outside of its local scope, we have to use pointers as function parameters. Using pointers to objects allows us to pass them to functions and avoid making copies of them, which saves memory and time. When memory is allocated dynamically, the new operator returns back a pointer or address of the brand new object in memory. So again, we need to be able to use pointer to deal with dynamically allocated memory. Arrays of variables contain multiple elements, but to be able to navigate through individual elements, like stepping through them in forward or backward manner, we again could apply pointer arithmetic and use pointers to access individual elements of an array. We can also envision a structure such as a list. For instance, we could create objects, and these objects could have pointers, pointer variables stored in them, and we can arrange them in such way that one object is pointing to the next one, and this one pointing to the next one, and so forth right here. So this would allow us to organize a list of objects which are aware of the presence of other objects. So these are called dynamic data structures. Similar data structure is a tree where an object or the actual tree is constructed from multiple objects which have pointers to each other in this manner. There are also other technical reasons why we need to use pointers. For example, overloading object constructors, operators, and to achieve polymorphic behavior in situations where objects are involved in inheritance relationship, we have to use pointers to simply access these features of the programming language, and we have to use pointer in these situations in our code. It is good to know that not all variables have the same size in computer memory. For example, an integer data type may require 4 bytes to be stored in memory. At the same time, a short integer, which is indicated by this short keyword, could occupy less space in computer memory. For instance, this integer, a short integer, could be allocated as a 16-bit integer. On the other hand, a double right here is likely to occupy 8 bytes on most modern computer architectures. So it's the larger object. And the pointer itself is also a variable. So for instance, we have already seen earlier in our presentation that if we build our code on 32-bit platform, the pointer is 32-bit size. But if we try to use a 64-bit platform, the pointer size changes to 64-bit, or allocating as many as 8 bytes in computer memory. So this is just something that we need to be aware that the data types do have specific sizes, and they may change from one platform to another. So the integer on one platform can be allocated as 32 bits, but in some other environment it could be a 64-bit size object. Our final slide is showing us a summary of syntax and the idea that pointer is a variable. That type of variable is holding a memory address and is designed to access other types of objects in computer memory indirectly. So the pointer remembers the data type that it points to, because when it's declared as a specific data type, whether it's a pointer to an integer or a character or a double and so forth. And so these are the summary syntax variety that you can see in different programming fragments which are using memory addresses and pointers.